Okay, this is our last boards go up, please, for the year. That's crazy. Um, we're gonna do two problems. That's it. Not crazy long. And then I have a little survey I want you to fill out. Also, hopefully not crazy long. But this first one, we're just gonna find the mass. I'm not gonna do the center of mass. But we got this thing that is bounded by y equals 1 minus x squared in the x-axis. And I give you a density function, and I want you to find the mass. So let's see if you can remember how to do this in 2D. Go ahead, hit pause. All right, let's scroll down. The x center of mass is, sorry, I guess we're just doing the mass. The x center mass is 0 because of symmetry, but let's find the mass. I'm going to set up the double integral of the density function dy dx. This is one that we're going to do in rectangular. I cut the region in half so that I wouldn't have to deal with the absolute value um, on the axis, and you know that it's totally symmetric. So at least from an x perspective, so the right half and the left half are going to weigh the same. We're going to have the same mass. So I do 2 times integral from 0 to 1, and then the integral from the bottom to the parabola of xy dy dx. My integral is let's see, we're integrating with respect to y. So it's x times 1/2 y squared, evaluated from 0 to 1 minus x squared. This is a y value, so is that, which gives me x times 1/2. And then I get 1 minus x squared squared, which is 1 minus 2x squared plus x to the 4th. It's FOILed. Careful with your negatives. And then I got 2, and then this guy slides in there. So this cancels with that, which is convenient. And it's just some simple power rules. A half, a minus a half, a 6. Evaluated from 0 to 1 makes it so that the powers don't actually matter. So we just add a half, a negative half, and a 6, and we get a mass of 1/6. Hopefully that's good and you remember that. We're not going to do the center mass part, so we will go on to the next problem. All right, little Green's theorem here. We got this terrible thing here, this terrible vector field. I want to find the integral of f dot over dr that, or the work, that's work, around the perimeter of a disk of radius 5 centered at the origin. So see if you can remember your Green's theorem. All right, let's scroll down to the answer. Here's my m, here's my n, right? Remember, I do the integral of the curl. The curl is n sub x minus m sub y. So my n sub x is this thing, whoop, which looks really bad. But my m sub y is this thing, and the terms here and here are in both of them, so they're going to cancel out. And then this is going to get combined with that, because I do this minus that. There's a double negative. So I get that the curl is 4 minus y squared. So it takes this absolutely terrible vector field, makes it so that we only have to work with this thing here. So I'm going to do the double integral over r of the curl of f dA, which is this dA. It'd be nice if we could stay in rectangular because these are nice. It's a nice power rule, easy to integrate, but we definitely want to go over to polar because of the bounds. So I'm going the full circle, so I go 0 to 2 pi. And I'm doing 0 to 5 because that thing has a radius of 5. I replace y with r sine theta. So that's a y squared, so I get r squared sine squared theta. And then I get a r d theta. My integral is easier because it's just the r's. So it's just some power rule. Maybe the sine squared theta there gets treated as a constant when I'm integrating with respect to r. So I get this guy. This is power rule on that piece and that piece. 2r squared minus 1/4 r to the fourth times the sine squared theta. Evaluated between those two bounds, it gives me this. Of course, you could use a calculator to do that. Arithmetic if you want. From there, I guess here I already did the conversion here. When I go to do my outer integral, I got to get rid of that sine squared theta and turn it into, with a power reduction, 1 minus cosine 2 theta all over 2. You may say, why isn't this over 2? Well, it's because this was 625 over 4. I already had a messy fraction, so I just took the over 2 and put it out front. 4 turned to an 8. It gives me this thing, which then that is integratable using some power rule there and some trig stuff there. Gives me this, which from 0 to 2 pi, this guy is going to give me that 225 pi over 4 with the negative, and then the sine 2 theta, very conveniently, between 0 and 2 pi, both of them are 0, so that goes away. So I get this answer here. So I thought about putting some more in here, but I figured this was good enough. I think that all y'all should be really proud of what you've done so far, or what you've done this year. You all have done a great job. Like I've told you many times, we have actually gotten further in this course than I've gotten in any other courses because we went faster first semester. So all this interruption that we had second semester, I guess we were ready for it. It would have been really, really exciting to get a lot further. I was like so psyched to do that, and to finish the three-dimensional. There's curl in 3D, um, and divergence in 3D, and they show up in physics all the time. Div, grad, curl, all that. But if you want to go and take a look at some of that on your own, feel free to do that. If not, you should still be super psyched about everything that you've done thus far this year. You guys have all been awesome. I've enjoyed our time together. Juniors, we'll pick it up again next year. And seniors, good luck. Come visit sometime. I would love to see you all when it is safe. So thanks again. And I have a little survey for you to fill out, so I appreciate that. And I will see you later.